So this is EE69AG, lecture 24, and we are designing a ring oscillator with 2 GHz frequency. So the frequency of a ring oscillator is given by 1 by 2n times Td. The design variables that we need to decide are what is this value of n. The Td is going to be a function of the W and L of both NMOS and PMOS. It will also be a function of any capacitance that we add at each node, right? Now, if we knew how to choose this W by L, how to choose this N, CL, etc. in the first go, that would be our starting point, right? But it's not a very easy decision to make. Therefore, we start with a reasonable starting point. We begin with a reasonable starting point as our ring oscillator, and from there, using some simulation results and some theory, we'll proceed to our final oscillator, right? So how did we begin? What was our starting point? We chose n to be the minimum value, right? So we chose n to be equal to 3. Then the second decision we made was we started off with minimum W by L for both NMOS and PMOS. Then we accounted for all the load capacitances, right? And if this was our ring, we called the total capacitance at this node as some C total, right? And this consists of the self capacitance here, the gate capacitance at the next stage, and any load capacitance that is coming here because of the inverters that you have connected here to account for the loading. After we have done so much, we then sized the W by L of the PMOS for equal drive strength. Right? And then we simulated for what is the F0 of this ring oscillator, and let's say we found that the F0 is much higher than what we wanted. We wanted 2 GHz, let's say this came out to be around 20 GHz, right? Much higher than what we want. Now, what is the power of this oscillator? In terms of C total, VDD, frequency F0? That will be equal to n times the capacitance at each node into VDD square into F0. Okay. So now our aim is to bring down this F0 to, let's say, some F0 by M. Okay. And we discussed 4 methods using which we could achieve this. Do you remember the 4 methods? We can add some capacitance, additional capacitance at each node, right? This would increase the delay of each stage, which would then decrease the frequency of oscillation. Or you can increase the number of stages in the ring. You could increase the length of the transistors. And finally, you can add a divider. Okay. And we said we were going to compare all of this in terms of the power, area, the supply sensitivity, and phase noise and jitter. Okay. You can add in a lot more metrics for comparison, but for now we will specifically focus on power, KVDD, and phase noise. Okay, so first we will simply look at how the power is varying and by how much a parameter has to be changed so that we can go from F0 to F0 by M. Okay, so let's say you are increasing the CL. That is, you are adding an additional capacitance to the output of each inverter. If I want to take the frequency from F0 to F0 by M, by how much should you increase the capacitance? Feel free to discuss and then answer. So 2 questions. One is by how much should you increase the capacitance, or what value of additional capacitance you need to add at that node. Second question is, how does the power change? So power from P0, what does it become after you make the change? Feel free to discuss and then give me an answer. So what is M times? So your C total has to increase by M times. Why?
It is 1 by proportional to 1 by TD, right?
It is proportional to 1 by TD.
TD is like proportional to
F0 is proportional to 1 by TD and TD is proportional to C. Right? So this means your C total has to increase by M times C total. Right? Which means you will have to add an additional capacitance given by M minus 1 times C total. Because C total is already there. Right? So you have to add so much capacitance in addition. Is there a quick way to recognize what is the existing C total? Because once you know that, you can add the additional capacitance. Question is clear? So you will calculate all of these capacitances individually. So CGG of this. From frequency and time delay, but that requires, you will need to know the current. And yeah. So how would you, is there a quick estimate that you can get for C total? Once you know this, you can add that additional capacitance.
power equation.
Very nice. So the power equation is N times C total into VDD square F, right? You run a simulation. So let me call this as P0. Run a simulation. You have P0 value, N VDD square and F0 are known, right? So you will get a C total there. Do you think this will be accurate, or is it likely to? What is the error you expect? Like, what is the reason for the error? All of that gets accounted here.
Changes.
Let's assume VDD is constant, right?
Basically, CGs and CDs and all are dependent on the bias of the thing, right?
Correct. But right, we want to know what is the C total on an average during the entire rise. So you will get that C total from here, right? And you require the same value here also. So the question is, do you think you will make an error in estimating this average C total when you use this equation? If so, why are we making the error? Correct. So your power, when you run a simulation, you will also measure the short circuit power as well as the leakage power. Leakage is usually very small, but short circuit is going to be slightly higher than leakage. Still, you expect it to be smaller than the dynamic power, but all of these are going to affect the estimate of C total you get here. Okay? So, for a quick approximation, you will get a C total value here. You will plug in so much capacitance at each node, run the simulation, and that will tell you how close you are to the frequency. Now, based on that, you can recalculate and add more capacitance. Right? So this way you will reach the final point you require very quickly instead of running a lot of iterations. Yes. This will be in the order of gate capacitance. Yes. This will be in the order of femtofarads, provided it is not dominated by the load. Okay, what happens to the power? It goes N times. It remains same. Any other answers? So P0 was equal to N times C. So this was C total. VDD square into F0. F0 has gone down by M. Your C total has increased by M. In effect, there is no change. Right? So the power remains the same. Okay, so next factor is you are increasing.
M minus 1 C2 is the extra capacitance that I need to add.
Yes. So that the total capacitance becomes M times C2. Let's say you are increasing the number of stages. So by how much should your N change? M times. This is okay. You want your frequency to change by M, so you increase the N number of stages by M. What happens to the power? No change?
Yes, that will be one problem, right? You cannot do that. All given one you are.
So what you'll do is you'll find out what is M times N. Now, if that turns out to be an even number, you will choose the closest odd number. That's it. How does the power change? So let's start with the expression for P0. This was equal to C VDD square N times C VDD square F0. How do you think the power should change? M times, okay, but F0 can be written as 2 by N times TD, right? So this becomes C VDD square by 2 times TD. Your power expression is independent of the number of stages. So the power remains the same. Okay, so the next step is wherein you are increasing the length. Why don't you tell me by how much we need to increase the length and how the power is going to change? So length has to be increased by M times. Everybody agrees? Okay. Let's say I increase my length by K times.
No, its capacitance is also changed.
So if I increase my length by K times, right, the current reduces by K times and all the capacitances, all the self capacitances will increase by K times. My delay is proportional to C by I. So this will become K square C by I. Right? So if I want to change the delay by M, I have to increase the length by root M. Right? So you increase the length by root M. What happens to the power? Yes?
Depends how C total is different.
Let's assume that self-capacitance is dominating for now. Then what happens? Remains the same? Everybody agrees? We'll see. Any other answers? 1 by root. So it reduces by root m. So power is again n C total into VDD square into F0. F0 has gone down by m. This has gone up by root m. Right? So the new power will be equal to P0 by root m. So power is reducing. And what about the final step where you are adding a divider? Right. So again, you will have to add a divide by m in the stage, right, at the output of the ring. So you will have the oscillator divide by m, and this is now your output. So the new power will be equal to whatever was the power we had earlier plus the power of the divider. So you expect to see a increase in the power. Okay, so now before I proceed with analyzing the phase noise of these different circuits, one very quick question. So let's say I had a ring like this, and say I also wanted to make sure that all these phases are separated by equal delay, right? I'm interested in checking all the phases of the ring. So we already said that we will ensure that any load seen by these inverters is going to be equal, right? But the moment you lay it out, you can clearly see if you lay it out like this, the routing length here is going to be smaller than the routing length here, which means the parasitics, the routing resistance and the routing capacitance is going to change the load seen by these inverters. Any recommendation on how we should lay this out such that the routing parasitics are also identical? Symmetrical. So how do I make it symmetrical? Okay. So generally we prefer 90-degree routings in a layout. Right, you have all done standard cell layout, right? So you don't do 45 degree, 60 degree. So it's all horizontal or vertical routings. So given that information, how would you? It's not that it is impossible. For example, for inductor and very, very specific cases, you can do it, right? But it may not always be possible. So we generally stick to 90-degree routing. Then how would you do this? One by one meaning? Then okay. So now I have to take this and feed it here, right? That will be a longer routing. You are commenting like this is what you are suggesting, but then this routing is going to be much longer. That is for clock. This is not very complicated, it's just very logical. You will intentionally increase this distance. This is a reasonable answer, but you can combine it with another but there are only 3 inverters. So you take one inverter to the bottom, right? So have something like this, and then you can increase the routing here. Your solution of increasing the routing for in-between nodes was also very valid, but just that you had a longer routing at the bottom, right? So you will additionally increase the routing by a lot. Now in this, the routing you need to add here is going to be slightly smaller. Right? So this way, when you lay out things that need symmetry, you have to be extra careful. Okay, so now we have to move towards analyzing how the 4 methods we discussed now is going to affect the phase noise of the oscillator, right? So let me bring in some additional information first, and then we will come to that analysis. Let's say you designed an oscillator, right? This had an this is given by, let's say, cos of omega naught t plus phi n1 of t. Okay? So this phi n1 of t is your phase noise in time domain, and as usual, we will work with its PST. Let's say it's given by S phi 1 of f. All right, and you find that the phase noise of this oscillator is higher than what you wanted in that particular application. Is there anything that you can immediately do without having to put any thought about its architecture to bring down the phase noise? If you design any circuit, let's say in 610 or 613, and you see that the noise is high, why compensation? So you see that the noise is high and you don't want to change the architecture. You are in the last minute of tape out. What is the one thing that is guaranteed to give you lower noise? You increase the power, right? You burn more power in the circuit. So let's quickly check if that is true for phase noise also, right? So what I'm going to do is I take one more oscillator, right? Identical to the same oscillator. So its output can be given by some V0 into cos of omega naught t plus phase noise. But because in time domain they are totally random, I can't write phi n 1 of t. If I write that, it means for a given time instant, the phase noise in both the oscillators are same. Right? So I can't do that. So I'll write phi n2 of t. Now, if phi n1 of t had a PSD S phi 1 of f, what comment can you make about this PSD? It will be the same, right? Is that clear? So this, let me simply call it as S phi of f. This will also be S phi of f. So now, let's say I sum up both these and I get some V out here. What I want you to do is, you derive what is the expression for V out and find out what is the phase noise in this. And see if there is any benefit in doing this experiment. You can assume narrowband FM approximation in solving this.
This S, right? So it will be 1 by 4 plus 1 by 4. I was correct this one.
You are correct.
Yes.
Right. So your V out will be equal to, I'll take V naught outside. There is cos of omega naught t plus phi n1 of t. So you'll have cos omega naught t cos phi n1 of t minus sin omega naught t into sin phi n1 of t. But you apply the narrowband FM approximation. So cos of phi n1 of t becomes 1. Sin of phi n1 of t becomes phi n1 of t. Right? So what do you get? You will have cos of omega naught t from both of these expressions. So that gives you 2 cos omega naught t minus, we'll have phi n1 of t plus phi n2 of t into sin of omega naught t. Is this okay?
You will apply that formula, right? Cos A plus cos B plus cos A plus cos B plus cos of 2 times cos of 2.
You can apply multiple ways to it. So now let's say I take 2 outside and then I'll have a 2 here. Now I apply that narrowband FM approximation but in reverse. Right? So this will be equal to 2 times V naught into cos of omega naught t plus phi n1 of t plus phi n2 of t by 2. That's it. So if you expand this using the narrowband FM approximation, you will get this. Now, this portion is the phase noise in the output. Right? I need to take the PSD of that. So this 1 by 2 will give you 1 by 4. Right? This is in magnitude, so you need the power. So this becomes 1 by 4 into S phi of f plus S phi of f. Okay. So this simply becomes S phi of f by 2. Okay. So in adding 2 identical oscillators, you have basically burnt twice the power, right? And as a benefit, your phase noise is becoming half. Is this clear? Now in practice, we don't make multiple VCOs and then add them in parallel. What we do is called as linear scaling. So let's assume that you have a circuit. There are transistors with some W by L. There is some current being drawn in every branch. There are impedances given by R, C and the inductance L. So these two L's are different, but I think everybody can recognize that now, right? So to reduce, let's say to reduce the phase noise by 2, you would double the current, right? Which is usually achieved by doubling the W by L's. Right? Now that the currents are doubled, if you want to maintain the same voltage level, all the impedances have to be halved. So you will do R by 2, 2C and L by 2. And in doing this, your time constants have not changed. So all your RC time constants and time constants associated with resistors and inductors, all of them are same, right? Therefore, you have double the power, voltage levels remain the same, time constants remain the same, but you expect to see a reduction in the phase noise. Okay? Sorry? So, the very basic principle is, if you double the current, you will see an improvement of 2x improvement in the phase noise performance, meaning the phase noise is going to become half. So in this particular scenario, right, this is actually very intuitive to understand. If you had burned a P0 here, now when you have two oscillators, you are burning twice the P0. Right. Okay. So if you have designed an oscillator, you find that its phase noise is higher than what you require. And if it's last minute, one thing that you can always blindly do is increase the power consumption. Do linear scaling, all the other parameters remain as it is, and you get a reduction in phase noise. Now, let me also show a very, very intuitive way of understanding how to relate the noise between a delay line and that of an oscillator. So let's say I take an oscillator like this. Sorry, I take a delay line. Right, I have three inverters. Now, if I take these three inverters and connect it in loop, this becomes your ring oscillator. Now, there will be some noise associated with all of these inverters, which is going to cause a phase noise for this delay line. I'm going to assume that three inverters are ideal, and I'll add the total phase noise here. Okay, such that the total phase noise appearing at the output is still the same. Let's assume that this has a PST given by S phi n dl of f. Okay, now I take the same delay line and I'm going to put it in feedback loop. So I'll assume that the same phi n dl is present here, and then I add it to the feedback loop and I get some phase noise here. That will have a PST given by S phi n of the oscillator. Will both of them be same? No? Can you find out the relationship between both of them? You can take a minute, feel free to discuss. You can ignore the parasitics of that line. Right? I just want to know what happens if I take a delay line, I put it into feedback. How does the phase noise profile change? Increases in what way? Increases part you are saying because you expect that phase noise in time domain to keep accumulating. Right? That part I agree. But can you also come up with the profile of S phi n of oscillator? By periodic, so I'm looking for the PST. Some relationship between these two PSTs. They can differ by? There is, so this has some F oscillation. This F oscillation will have a frequency error. That frequency noise, that I agree. Right? Can you calculate what that frequency noise will be? Maybe that is a good starting point. If you calculate what that frequency noise is, then you can integrate it and calculate what is the phase noise spectrum.
Is it something like the first one will be bounded and the second one will be bounded?
That is true. First one is going to be bounded, second one is unbounded. That we have already discussed. I just want to see a relationship between them. And this calculation is so simple and so intuitive, which is why.
Compare both, how can we write in the same equation when one side is bounded and one side is not bounded?
So when we say it is unbounded, what is unbounded? The power is unbounded, right? But I can still write an expression for the spectrum. Just that.
The integral will be.
Let me give you a hint. Right? Let's say the delay associated with this was TDL. In the absence of phi n of dl, right? What does TDL correspond to? Let's assume that T naught, if this phi n of dl was not there, then the oscillation was T naught, right? Let's say the ideal oscillation was T naught, right? And the actual oscillation frequency in the presence of phi n of dl, let me call it as T OSC, T oscillation, right? Can you find a relationship between T naught, T oscillation and phi n? In the absence of phi n, what is the relationship between T naught and TDL? Are they equal? 2 times, right? Or in other words, TDL was equal to T naught by 2. Okay. So now you have phi n dl. You can replace it by a delay, right? So now can you give an expression? So T oscillation will be equal to. So let me put it as T oscillation by 2, right? So this will be equal to TDL plus. Convert this into time, right? So this phi n of dl by 2 pi into T oscillation, right? Is this expression clear to you? Please ask if it's not. So earlier, this from the ring, you are going to get an output like this. Earlier, this part was equal to TDL, right? But now this edge is going to shift, right? So from the rising edge to the falling edge will be equal to TDL plus whatever is the jitter caused by this. Right? That's what I have written. I could also have written this in phase domain, in which case this would be equal to pi equal to, I convert TDL into phase domain. So that will be TDL by T oscillation into 2 pi plus phi. Right? You can use either of these. Now can you give me a relationship between F oscillation and F naught? So give me what is F oscillation equal to? In terms of F naught and phi n. What is this? Phi minus? Pi minus. Pi minus phi n by. So let me rewrite it a little bit. So this will be equal to F naught. Is there 2 pi here? You should get F naught by minus F naught into phi n by pi. You'll get this, right? Is there a confusion here? Okay. All right. Yeah. This relationship you understood? FOC relation. Okay. So let me start from this, right? This I can write it as 1 by 2 times FOC equal to, I will have to replace TDL, right? And how can I replace TDL? TDL is equal to 2 by F naught. TDL was equal to T naught by 2, right? Which means, 1 by 2 F naught plus phi n dl by 2 pi into FOC. Once I write it in this format, I think it is obvious. You can rearrange things and you will get F oscillation will be equal to F naught minus phi n by pi into F naught. Is it okay now? Right? So, can you see the simplicity of this calculation so far? All that we have said is from here to here, ideally it should have been pi phase accumulation, right? Or in other words, it is half the time period. But now in the presence of additional phase noise, that half the time period is going to change. And based on that, we have calculated the relationship between the new oscillation frequency and the old oscillation frequency. So the new oscillation frequency is F naught, which is the old oscillation frequency, plus some frequency noise, plus or minus some frequency noise, right? Now, you have an expression for frequency noise. Can you give me an expression for phase noise of the oscillator? What should we do to frequency noise to get phase noise? You have to integrate frequency noise in radians per second, right? So you will have to integrate 2 pi times the value of the phase noise given here, right? Which means, what is the PSD? Pi and pi gets cancelled. Feel free to refer to your notes. Let me take out all the constants out of the integration. So you'll have 2 F naught, then integral of phi n dt, and of course there is a minus sign. Minus sign will not matter when you take the PSD, right? So 2 F naught will become 4 times F naught square. Phi n will get replaced by S phi of F by S, right? And S is, so this is 2 pi F the whole square. So this gives you F naught by pi F the whole square into S phi. So this S phi is basically the delay line's phase noise of F. So this is a very nice way of thinking about how a delay line's phase noise is going to change if you put it into feedback. So all well and good, but what does this equation tell us? If you had a white noise profile at the output of the delay line, what happens to the noise profile at the output of the oscillator? It gets shaped by 1 by f square. So the full shaping function is f naught by pi f the whole square, right? So if you started with white noise, you end up with 1 by f square noise profile. What is happening is you start with some profile at the delay line. Frequency noise at the output of the oscillator has the same profile. To get phase noise, you integrate it, because of which you get a 1 by f square function. This is okay? Okay, very good. So now I will give you the final expression for the phase noise in a ring oscillator. Before I give you that final expression, I just want to give you some intuition as to where it is coming from. We won't be able to derive it in this course, right? So I take an inverter. Let's say I give a rising edge. Corresponding to that, the NMOS is going to pull out charges from the capacitor, because of which you will have a falling edge. Now, what do you think? Assume that the rising edge is jitter-free, it's ideal. Why do you think there should be a phase noise at the output? Which of these transistors is contributing the phase noise? NMOS is contributing to a phase noise. Why?
It's taking time to discharge, right?
It's taking time to discharge, but if there was, time is not the problem, right? If there was no noise in the NMOS transistor, it will take some time to discharge, but that time is going to be a constant. It's not noise. So now the NMOS has noise, right? It has drain current noise due to both thermal noise as well as flicker noise, because of which the current getting pulled out has variations, right? And depending on how much that variation is, your edge might discharge in multiple different ways. And if I think of this point as my threshold voltage, then you can see that depending on how the voltage waveform is at that point, you can have a jitter. The first waveform happened to have zero jitter because of the way I have drawn, but you see where the jitter is coming out from, right? So your edge is going to shift at the threshold point, resulting in jitter. Do you think the PMOS has any effect, noise of the PMOS? Let's assume leakage current. Leakage current part I understand, but if there is no leakage current, does it have any effect? It has thermal noise and flicker noise, but it is cut off, right? It is completely off. Then does it have an effect? You are assuming subthreshold conduction, and because of that. Again, I agree. But let's say, again, because there is another factor which is causing the effect, right? A prominent effect. So to bring that out, let's say there is, once it is cut off, there is no noise, like pure cut off. Then is it possible for it to contribute noise? Gate to drain capacitance. This is assuming there is a supply noise. Right? Supply noise and a capacitance. Okay. So let me bring out the point I wanted to bring out. Right? So during the time during this period, when the NMOS is completely off and PMOS was on, right? PMOS is basically in linear region, acting like a resistor. Right? So it will have its own thermal noise and flicker noise even during that period. Because of that, the value here is going to fluctuate. Now, let's say at this edge, it got completely cut off. Now, the starting point from which the voltage is dropping to zero, that depends on the noise when it was. So, based on that, your waveform could either look like this, or if that noise was like this, it could look like this, etc. So that is also contributing to jitter. That noise will be part of. Yeah. So it's because of the PMOS. So that PMOS, that voltage becomes the initial voltage for the capacitor, right? From where you start to discharge. Is that clear? Right? So this way both NMOS and PMOS are going to contribute to the noise of the capacitor. Now the other reasons you said, noise during subthreshold conduction, the CGD, supply noise, all of those are true, but wanted to show you that even if noise was not there and transistor was ideally in cutoff without any current flow, you still have these problems. Okay. So now I'll give you the expression. So this is the expression for phase noise for an n-stage ring oscillator. I'll give you the expression and then explain what each terms are. So we will split this phase noise into two regions. The one where white noise is dominant. So the white noise profile of the phase noise is going to be F0 by F the whole square into 1 by 2 ID square Si of NMOS plus Si of PMOS plus 2 KT by ID into VDD. Then S phi of flicker. This is equal to F0 by F the whole square 1 by 4n ID square into S of, you don't have to remember this by heart, but given this expression, so you should be able to analyze how a change in parameter is going to affect the noise. For your end semester, you will be allowed to bring a cheat sheet. So now it's up to you to figure out what all equations you have to write. I'm going to assume that you have written all the required equations on that sheet. Okay, so these are the two expressions. Let us start with the
what is the second term contribution for?
So this is the flicker noise.
Not the above and the second term.
This contribution is coming from this factor. So if you had a rising edge, right, the drain currents of these are going to cause a fluctuation in the falling edge, right? Different drain current is going to cause how the edge is falling. Now this portion wherein the PMOS.
Where is the marker? Cannot see the marker.
This is okay. So the NMOS current is going to determine the fluctuations happening during the falling. The PMOS noise is going to determine what is the starting point.
This is the first term, the SIN of that.
The first part is the current determining the shift in the edges. The second term, so how it comes out is, if you remember, if you had a resistor connected in parallel, if you had this sort of a configuration, right, a voltage source, a resistor and a capacitance, right, wherein you model the voltage noise of the resistor like this. This average noise here was going to be KT by C, right. The PMOS current affecting the starting point has a similar effect. It determines the starting point, and that is getting stored on a capacitor, right? So that has a similar effect as the KT by C. So this portion is coming because of the thermal noise drain current affecting how the capacitor is charging or discharging, and this portion is coming based on how the other transistor, which is not involved in charging or discharging, is affecting the starting point for the capacitor. Alright, so let's quickly look at what each of these parameters are. F0 is the oscillation frequency. F is the offset frequency. Do you remember what is the offset frequency? Feel free to refer to your notes. Any answers? What is the offset frequency? If you think you are sitting with the wrong partner for discussion, feel free to change. If we have to report the phase noise of an oscillator, right, you need to know what is the F0. What is the other thing that you have to know? How do we report the phase noise for an oscillator? How does the phase noise of an oscillator look like?
You look like F1 and square.
That's a spectrum, but let's say I expect an oscillator to be oscillating at F0. Ideally, I expect to see a sharp impulse, right? But in practice, you would see that there is power distribution around it, right? Now, this profile, this skirt is basically your phase noise, right? And how did we report it? We would identify an offset frequency and report the value at that frequency, right? So right now I am saying that this is your F. So you are reporting the value at F0 plus F. If I were looking only at the phase noise profile, now the whole thing will be centered at 0 and you will have a profile like this and you are reporting the value at some F. So this is that offset frequency. Okay. ID is the drain current. We calculate the drain current of NMOS and PMOS for a very particular operating point. And that operating point is given by VGS equal to VDD, VDS equal to VDD by 2. I'll put mod here because the same holds true for both NMOS and PMOS. Okay. SI NMOS is the two-sided PSD of the thermal noise current. Can you give me the expression? For kT gamma gm is the one-sided PSD. So the two-sided PSD becomes 2 kT gamma gm. Right? K is Boltzmann constant, T is temperature, ID is again the current through the transistor at this given operating point, VDD is the power supply. Okay. Again, you don't have to remember this equation by heart, but given this equation, we should be able to analyze how certain changes we make in the design are going to affect the phase noise of the output. So let's take this equation. Let's see what inferences we can make based on this equation. So we are going to look at how this S5 white is going to change, but after normalizing it to F0 by F the whole square. The reason for normalizing it to this factor will become clear by the end of this lecture. So basically we are looking at only this factor. Okay. So this is a n-stage ring oscillator, right? Let's say I increase my n. What effect do you expect to see in the white noise profile? Nothing, right? It is independent of n. So you increase the n, you will see no change. Okay. What if I add an additional capacitance? How does this change?
ID. ID.
No change? Let's say I increase the ID. Decrease by how much? Okay, if this term was dominating? So if I increase it by m? Okay, what about if this term was dominating? Why? 1 by m, right? There is a gm here. GM is also, so I can write it as 2ID by VGS minus VTH. Because we have calculated all of these for a particular operating point, I can replace this VGS corresponding to that, and that was equal to VDD. Okay. So both these terms are going to reduce by 1 by m. So this becomes 1 by m times S5 of it. Any questions on this? So then we move on to the flicker noise expression. So again, F0 is the oscillation frequency, F is the offset frequency, N the number of stages in the ring oscillator, ID is the current through the transistor calculated for VGS equal to VDD and VDS equal to VDD by T, same as before. S 1 by F of NMOS is the two-sided PSD of the flicker noise current. Okay, so let us look at what that expression comes out to be. So if I take an NMOS, let's say there was some Vn here. What is the expression? So this is corresponding to the 1 by F noise, flicker noise, right? What is the expression you know for this?
4K CW by L. W into L.
Into W into L? Refer to your notes, right? Expression for flicker noise.
Constant K on WL.
Okay, let me call the constant as K upon W into L. So this 1 by F part, I hope everyone remembers, right? It's called as 1 by F noise, flicker noise. We are missing one factor here. COX. Right? So this is your one-sided PSD. Can you give me the two-sided PSD? By half. So this will become K by 2 times WLCOX into 1 by F. Right? Now, for now you can assume that this is grounded. Can you tell me what will be the current noise associated with this? So I'm looking at SI 1 by F of F. What is the, if this was Vn, what would be the current here? GM times Vn. Right? So the transfer function is GM. Therefore, you have to do transfer function square. So this gives you GM square times K by 2 WLCOX into 1 by F. That's all. So I'll replace this in the total expression. So this becomes Kn into Gmn square by twice of WLN of COX. This will become Kp into GMP square by twice of WL for the PMOS into COX. Okay. We are interested in figuring out how the parameters are going to change as you change W and L. So for now, I'll simply assume that the GMN and GMP are equal, right? Which means I can bring it out and I'll write this as GM by ID the whole square. Did I make a mistake in writing this equation? I missed out the 1 by F, right? So this becomes F0 square and you'll have F cube. Still with me? Okay, good. So now let's do some inferences on S5 flicker, again normalizing it to F0 by F the whole square. I increase the n, what happens? It reduces by n, right? So this is proportional to 1 by n. What happens if I increase the gate capacitances? So I am increasing the W, L, COX, the whole term together, right? The gate capacitance. It decreases, right? So this is inversely proportional to the gate cap. Let's say I add an additional CL to the node. Then what happens? Then no change. Is that okay? There is no CL here, right? Only WLCOX is appearing in the denominator. So this is independent of CL. Okay? So now let me quickly give you a question. Let's say you have an oscillator. This has some frequency F0, has a power consumption P0, and has some phase noise PSD given by S5 of oscillation F. Assume that all the capacitances are dominated by the self-capacitance. I make all the W by L's to be twice the original value. Can you tell me how F0, P0 and this factor are going to change? Yes, right now. You have the expression for S5 of oscillation. You'll have to check for S5 white and S5 flicker separately and then give me a comment. Again, feel free to discuss. So let's conclude. Your F0 remains the same. P0 becomes twice of P0. S5 white will become half of the original value. And why is that happening? Because you have ID here and you have one ID will remain here also. So this ID and ID square will cancel and you will have one ID remaining, right? Because of which the S5 white is reducing. And S5 flicker is also becoming half. Why is that happening? The GM by ID effect will cancel out, but you have a W here. So because of that, that is also becoming half. Which means overall, your phase noise at the output of the oscillator has become half. And if you look at this example, this clearly shows how the linear scaling is working out, right? You have doubled your power and you got a benefit in the phase noise of the oscillator. Okay, perfect. Now we have to compare how the phase noise of the different ring oscillators are going to be. But do you immediately see a problem in directly comparing the phase noise?
Power is not.
Right. So if I have two architectures, even if they are burning different powers, the one with higher power consumption is likely to have a lower phase noise. So if I want to skew the result, right, I have A, architecture B, and I'm intent on showing that B has lower phase noise, I can simply burn more power there, right? But the comparison is not fair. So now to compare, we need to normalize things, right? Yeah. So you need to normalize it with respect to P0. What are the factors do you think you should normalize to? The phase noise expressions are also proportional to the oscillation frequency, right? So you should also normalize it to the oscillation frequency, right? So let me give you a metric that takes into account all of these trade-offs, and this is what we call as a figure of merit. In short, called as FOM. Now, you can have different figure of merit definitions for different circuits. ADCs will have its own figure of merit, oscillators will have its own figure of merit, etc. So, I'm going to give you the expression for the figure of merit of an oscillator that takes into account this power phase noise trade-off. Okay. So, this will be equal to 1 by power into phase noise into F0 by F the whole square. This power is usually represented in milliwatts. Okay. What is PN, phase noise? So now you will report your phase noise at a particular offset frequency, right? And that offset frequency has to appear here. So now in comparing the 4 architectures of the ring oscillator that we have come up with, we will directly compare for the FOM and see which of those architectures is giving you a better FOM. Okay, so let me quickly rewrite this equation so that it becomes easy to use the result we have derived so far. So this is power in milliwatt into Pn divided by F0 by F the whole square. We have seen the relationship for this factor earlier. All okay so far? Okay, so now let's go back to our 4 different methods. Let's say I added a capacitance externally. Okay. Can you tell me what happens to the FOM? So in doing this, you will have to first check what happens to the power and what happens to the phase noise. And in comparing for phase noise, you will have to check what happens to the flicker part of it and what happens to the thermal part of it. So by flicker part, I mean the portion with 1 by f cube profile, and this is the 1 by f square profile. So can you tell me this result and then we can break. So what happened to the power? Power? Go back and check. We have done this in the beginning. So to obtain this, we had to make sure that our C total had increased to M times C total. Power is equal to number of stages into C total into VDD square into the frequency of oscillation. Frequency of oscillation has reduced. Power remains the same. Right? So now can you comment on the flicker noise part? The 1 by f cube noise profile. Was that a function of additional capacitance? So this is the expression for flicker noise. Did this depend on the additional capacitance? No. So the 1 by f cube noise remains the same for the oscillator. What about white noise? This also remains the same, right? Which means your FOM is going to remain the same. Is that okay? Okay. So for next class, please think of whether it is good to have a larger FOM or a smaller FOM, and whether your FOM is going to change as your F changes, the offset frequency. Right? And then we'll start from this point onwards. Thank you.